multiple random variables. So question number 1a, joint distribution of two or more random variables. This is 2 marks question. So we are going to draw the distribution between two or more variables. Let us take example in a room which has two variables which are varying its temperature as well as the intensity of light. So the joint behavior of two random variable for a discrete or continuous x and y may be defined as a joint cumulative distribution function fxy of x comma y for the probability x less than or equal to x and y less than or equal to y. So in an n dimension case, the probability of that random variable varies from x1 to xn. Next, in properties of joint distribution function for a random variable x and y, so the joint distribution function ranges between 0 to 1, which is given by fxy of x comma y is probability of x less than or equal to x and y less than or equal to x. So if you apply the limits between minus infinite to infinite for the variables x and y, the fxy of x comma y is equal to 0 and fxy of x comma y is equal to 1. Next problem in joint density function. Here the joint density function of a random variable x and y is given as fxy of, it is a small joint density function now, so it should be represented with small fxy of x comma y is equal to 8xy for 0 less than or equal to x less than or equal to 1 and 0 less than or equal to y less than or equal to x, and it is equivalent to 0 otherwise. So can you find out that margin density of x, marginal density of y, conditional density of x and conditional density of y. So while calculating the marginal density of x, the formula for that is fxy of x is equal to integral 0 to y is equal to x. Now you substitute that value of fxy of x comma y here, then 8xy. Here the term y is a constant, here the term x is constant, so take it outside 8x and the integration of y is y square by 2. If you substitute the value of x here, then it becomes 4x cube. Similarly, find out for the marginal density of y, which is an integration of x to y to 1. So in going to the conditional density of x and conditional density of y, fxy of x by y is equal to fx of x fx by fxy. In going to conditional density of y, f of y by x is equal to f of x intersection y by f of y. So in going to the conditional density function, question number 2a, the conditional density function derives from the derivative. So density function now we have to represent with small f. If you differentiate the distribution function, we will get the conditional density function, and the corresponding response looks like this. So question number 2b, explain about the joint probability matrix. So the probability of matrix can be represented in a, this is a two-dimensional discrete finite probability scheme. Here the joint probability matrix of the random variable x and y associated with the space 1 and 2 is p11 p12 up to m. So here this is n cross n matrix, so I am going to represent like this, right? In going to the statistical question number 2c, if it is a statistical independence, we have already studied the statistical independence in probability. If the both are independent of to each other, probability of a intersection b is equal to probability of a into b. Similarly, like probability of x and y are the two random variables with joint probability of mass function, probability of x and phi, and the marginal probability mass functions is m of x and n of y respectively. The random variable x and y is going to be statistically independent if and only if the probability of x and y is equal to m of x and n of y for all the values ranges from x and y.